In this video, I want to demonstrate how you should approach the topic of designing a glass partition with good sound insulation. In this case, we're looking at a school, so let's get into it. This is like the classroom, and then you have the corridor out there, and then we have a door, we have a side light, and we have an above light here, and you have a wall construction. So when you're dealing with sound insulation here, the typical requirement in Swedish schools is 40 dBs from corridor to classroom. Now, how will you approach that? I mean, one way would be if you make sure that all the components have more than 40 dBs, and then you will probably be fine. But that might not be practical, because in this case we have a glass door, and a glass door is difficult to get good sound insulation. You can find, I think, up to let's see if this one is correct. Draw freely, then yes. No, wait, draw on model. RW38. You can find that. And also another one is accessibility, because you don't want to have thresholds. You want to have threshold-less design on the door. This one should be flat for many reasons. And that means you will have some kind of mechanical threshold that when you close the door, it comes down and makes it an airtight seal, and that way you can have good sound insulation that way. But anyways, we need to get up to R prime W. That's when you have the total sound insulation that the sound reduction from the corridor in here. That is a composite index of all the transmission paths. So the door is just one of them. But then you might choose a side light here. Draw model, red, yes. And this one you could go up. It's easier to construct a glass partition with higher sound insulation compared to a door. We'll do these ones also. 43, like so. And then the wall itself could be even higher, perhaps even RW 48 to 52. Oh, no, wait, just let's do one for clarity, like this. 48 dB wall, 43 on the side lights and above light, and 38 on the door. So you see there's many different sound reduction indices here, and each of these correspond to a different transmission path. And then there's another one that you must not forget. That one, it might not be an issue in the case of a corridor, but you will also have this path to consider. Don't forget about that. The plate, because here we have, this is now we're in the ground below. Let's go back up into the classroom. This transmission path, my friends. Flanking transmission through the plate, through the foundation. And this one can perhaps be quite high. It depends on the thickness of the plate. So in this case, what could it be? I'd say it's let's say it's 58 in this case. This with drawing in 3 dimensions, that's really a challenge, but it's really cool also when you can see everything like this. And then of course you will have some transmission perhaps through the ceiling construction as well. What goes on up here? Here you will have flanking transmission also. And in this case, now maybe the ventilation guys haven't finished yet, but there's probably going to be some ducts coming with fresh air as well. So, and each of these transmission paths will add another reduction index. So I don't know, what could this perhaps would be 52 or something, let's say. No, we don't see that one from down here, but we keep adding and adding. But anyways, in this specific case now, let's go out into the corridor and have a look what it looks like. Because, okay, yeah, you see what's this. The glass partition is a significant part of the entire partition here, because this is the common area between these two rooms. And the glass consists, it's like 90% of the total is just glass. So even if we make a wall here that is RW 60, it will have no effect because it will all go through the weakest link. And this is similar. I like the comparison. If you would construct an electric circuit, even if this is 48, it doesn't matter because these ones will determine it all. So in this case, you might not even, perhaps not, it's not enough with the 38. Maybe you have to find some special law and go even higher for the reason that it's such a big part of the total. But so let me draw a little analogy. Let's do some graffiti on this wall. Draw a model. And let's say we have an electric circuit here. And then you have two resistors in parallel connection like this. And now, if one of these, let's say that this one is 1 mega ohm. Oh, yeah, it looks like 1 micro ohm. That was not my point here. Nay. Oh, crap. I pushed the clear button. I didn't want to do that. Oh, well, anyways. Let's do it again. Electric circuit. Resistor. Add a second resistor in parallel here. And we just call them R1 and R2. Now, if R1 is equal to 1 mega ohm. And the second R2 is equal to 100 ohm. What will happen here in this case? Well, nothing will come through here. It will 99.9% of the current will flow here through the weaker resistor. And this is the point. If you have a partition like this, it won't matter if your wall is really, really good. If you got the glass partition that is a significant part of it, everything will go that path instead. So, in order to have some kind of meaningful, these different transmission paths need to be on the similar magnitude. And you could do this as a parallel connection with an analogy and keep adding R1, R2, R3, R4, and each of them will correspond to the specific transmission path. Side light, side overlight, door, wall, flanking through the foundation, flanking through the ceiling, and you will have flanking through the sides and so on and so forth. And this is something that I really like about being an engineer, that you can find analogies. It's basically it's the same equation that comes again and again and again, even though we're working with acoustics here, but we can look at it as an electric circuit and you will still be able to solve the problem. And I think that is beautiful. All right. That was a little rundown on how you can look at flanking transmission and composite sound reduction indices in like an electric circuit. Hope you learned something today. See you later.